So we went through the rational zeros test on Friday. And we recalled that process of putting down our pool of numbers and then guessing and checking until we got one right. Okay? Sometimes we guessed a correct zero right away. Sometimes it took us a few tries to get one. Okay? So let's talk about two rules that will save us some time. Okay? One of these you may have talked about last year. I don't remember. Descartes' rule of signs. Do you remember that name? Okay. So don't feel like you have to write this down. This is me saying, hey, we have a polynomial. Okay? What I would write if I were you, if f of x is a polynomial. I wouldn't copy all of this down. This is just what a polynomial looks like. Okay? So if we have a polynomial with real coefficients and a constant term at the end, then this is Descartes' rule of signs. First of all, the number of positive real zeros is f of f is either equal to the number of variations in sign of f of x or less than by an even integer. Just write it down or paraphrase, shorthand notation, whatever you want, and then I'm going to talk about it. Okay, so this is only half of the rule. We're talking about positive real zeros. Okay, positive real zeros. Sign variation. What does that mean? As we're looking at our polynomial, what do I mean by sign variation, Gabe? Okay, so Gabe, you said x squared minus x plus 3. We would have two variations in sign because we go from a positive to a negative, from a negative to a positive. That is sign variation. Okay? Now, we count up the number of sign variations, and that is going to tell us how many positive real zeros we have, or an even integer less than that. Okay, so if we have 5 sign variations, we could have 5 positive zeros, we could have 3 positive zeros, or we could have 1 positive zero. Okay. Basically, you can just keep subtracting 2 until you get to 1 or 0. Let's talk about why there would be either that number or an even number less. Why is it an even number less? Jerry?
Because imaginary zeros come in pairs.
Okay, our complex zeros come in pairs, okay? So that's why we have to think about, well, there could be that possibility of a pair of complex zeros. So if there are 5 sign variations, it could be 5 or 3 or 1. Okay, now we are going to do the same thing for negative real zeros, except we are going to look for the sign variations in f of negative x. So it's the same process, except we look for sign variations in f of negative x. So why is this helpful? If we get, like if using Descartes' rule of signs, if it says we're only supposed to have one positive real zero, once we find it, we're not going to try another positive number. If it says that we're supposed to have no negative real zeros, then you're not going to plug in any negative numbers because you know that they're not going to work. Okay? Not all the time will it eliminate choices at the beginning. Sometimes it will. Descartes' rule of signs will more help us like as we go. Okay, if we know we're only supposed to get one positive zero, once we find it, don't try any more positive numbers. Okay? So let's look at applying Descartes' rule of signs to this polynomial. Okay, so to get the number of positive real zeros, we need to count the number of sign variations. So our first term is positive, our second term is negative, third term is positive, fourth term is negative. How many times do we change signs? We change 3. We go from positive to negative, negative to positive, positive to negative. But are we guaranteed to have 3 positive zeros? We could have 3, or we could have 1. We have to subtract 2. So we could have 3, or we could have 1. Now, let's look at our negative real zeros. For this, we need to look at f of negative x. Remember, f of negative x means we're plugging negative x in. Okay, what happens when we take negative x and we cube it? Negative x cubed. So we have negative 3x cubed. What happens when we take negative x and we square it? Positive. And so this stays as minus 5x squared. 6 times negative x, it's minus 6x, and then minus 4. Okay? How many sign variations do we have in f of negative x? None. So we will not have any negative real zeros. This is nice because when we write our possible rational zeros, we can automatically eliminate half the list and only focus on the positive ones. That's nice, isn't it? So we're actually going to go through and find the zeros to this function. Okay? Okay, so our possible rational zeros, factors of the constant term. 1, 2, and 4, right? Over factors of our leading coefficient. 1 and 3. So if I asked you for all of the possible rational zeros, you would write 1 over 1, 2 over 1, 3 over 1. What am I saying? Nope. 4 over 1. Getting in a rhythm there. 1 over 3, 2 over 3, and 4 over 3. Okay? We have 12 possible rational zeros up there. But with Descartes' rule of signs, we can erase 6 of them. I wouldn't erase them. I would disregard them. Because we know negative zeros aren't going to work. Okay? What do you want to try first? What did you always try first? We should always try 1 first. Okay. So we drop down to 3, multiply, add to get -2, multiply, add to get 4. Look at that. We have our 1 positive real zero. Now, what are our possibilities for the other 2? They could both be positive, or they could both be imaginary. Okay? Once you get to a quadratic, do not use synthetic division again. Never, ever, ever. Okay? At this point, we have 3x squared minus 2x plus 4. First thing we should try to do is factor. Okay, we have 3x and x. We know that since this is positive and this is negative, both of those have to be negative, right? Okay, so what about 2 and 2? That gives us -8x, right? One and 4. That's not any better. 4 and 1. That's not any better. We're stuck. Well, they're either imaginary or irrational, right? Do you know for a fact that they're imaginary? How are we going to find them? Well, they are imaginary. Quadratic formula! X equals -b plus or minus the square root of b squared minus 4ac all over 2a. What is 4 minus 48? -44. The square root of radical -44 would reduce to what? Yes. So square root of 4 can come out as 2. So we're left with 2 radical 11, and then that negative comes out as an I. I don't care if you write this as 2 radical 11i or 2i radical 11. I will be flexible. Okay? Remember, when you reduce, everything in the numerator has to get reduced by the denominator. So our zeros are 1 plus or minus 1 radical 11i all over 3. As well as x equals 1. Okay? So, Descartes' rule of signs, we knew we had 3 or 1 positive root 0. It turned out we had 1 because the other 2 were imaginary.
Do you want us to write the I answers like that, or like 1/3 plus or minus radical 11i over 3?
That would probably be better. Thank you for reminding me of that. So here are your zeros, because we do like A plus BI for our zeros, or for our complex numbers. Okay, questions? My understanding is you have seen Descartes' rule of signs.
Yeah.
Okay, perfect. Now, before we go to lunch, we'll just talk about the upper and lower bound rules, and then after lunch, we will apply them. Okay? So, what you need to write down here is that we are taking a polynomial, and we are dividing by x minus c. Okay? Using synthetic division. We're taking a polynomial and we're dividing by x minus c. Don't feel like you have to write every single word up there. We have a polynomial divided by x minus c. Oh, sorry. Okay. What I'm going to do is I'm going to put this up here for you to write down. And then once we have it written down, then we will focus on understanding what it means. Okay, so it is time for lunch. First of all, don't panic if you don't understand what this means, because we're going to talk through it. Okay, and I'll show you an example, and the example will help a lot more than me just talking about it. Okay, if you're not done writing it down, you can either stay right now and write it down, or just come back a couple minutes, like before 1 o'clock. I will start at 1 o'clock. So if you're here at like 12:58 and finish writing it down, then you can do that. Okay, enjoy your lunch. All right, so now that we're back, if we do synthetic division with a positive C value, and everything in our synthetic division, so we're talking about when we do synthetic division, these numbers down here. If they are all positive or all negative, then C is an upper bound for the real zeros, which means when you go to pick your next zero, don't pick anything higher than that C value. It's an upper bound. There will not be anything higher than it. Okay? If you have a negative C value, and the numbers down here alternate, then that is a lower bound, which means don't pick anything less than that number. Everything must be higher than it. Okay? So this can be helpful if you find a zero that does not work and it follows one of these patterns, then you might be able to cross some numbers off of your list. Okay? So I want to show you what both of those look like using this example right here. And what I'd like you to do is create a list of possible zeros for me so we can get started with this. Henry, can you read your list out for me? Okay. Can you hear your list?
Yeah.
Okay.
Plus or minus 1, plus minus 1/2, plus minus 1/3, plus minus 1/6, plus or minus 2, plus minus, or minus
2/3. Okay. How does that list look? Look good? Okay, for effect, I'm going to write these in order. Okay, now I wouldn't expect you to write them out like this on your paper. I'm going to so we can see how these upper and lower bounds work, okay? So when we go to try synthetic division with 6x cubed minus 4x squared plus 3x minus 2, okay? The first C value we're probably going to try is what? 1, okay? 1 is a positive C value, right? We drop down the 6. 6 times 1 is 6. We add it to get 2. Multiply to 2, add to get 5. Multiply by 1, add to get 3. Okay? So it doesn't work. However, what do you notice about the entire last row? They're all positive. Since we have a positive C value and our last row all has the same sign, that means we have an upper bound. Which means all of our zeros are going to be less than 1. So not only can we cross off 1, but we also know not to try what other zero? 2. Which could have been some of our next guesses. Okay, 2 is a nice number to plug in. All right. Since we had a positive C value and our entire last row had the same sign, it's an upper bound. Don't try anything higher. Okay. Now, I know that this is probably not the next zero you would try, but I want to show you what a lower bound would look like, okay? So let's say you do synthetic division. Okay, it didn't work for us the first time. So let's try negative 1/3. Okay, like I said, probably not the next one you're going to try, but for effect, I want to show it to you. Okay. So 6 times negative 1/3 is negative 2. Add to get negative 6. Negative 6 times negative 1/3 is a positive 2. Add to get 1. 1 times negative 1/3 is negative 1/3. Obviously, this is not going to be 0, but it is going to be a negative number, right?
Yeah, you have to get 5.
I add to get 5, and I didn't do that. How about negative 5? Right? Is that better? So our remainder is negative 11/3. Okay? Now, since C is negative, and these signs alternate, then we know this can be a lower bound, which means all zeros need to be larger than it. Hold on, Caroline. So not only can we cross off 1/3, negative 1/3, but also all the ones below it.
Does the pattern still work if your first one was a negative 6 and you had like a negative 1/3, and it was like negative 6 and then positive?
As long as it alternates signs, you're good.
But it doesn't have, it doesn't have to include the C and alternate.
No, it's just the last row needs to alternate. Also, if there's a 0, it could count as a positive or a negative. So if this were a 0 instead of a 5, we could still say that the signs were alternating. Okay? Now, yes.
It's the remainder count as well.
Yes. Would this have been a smart choice? To try negative 1/3? It turned out to be. Okay? Darby, do you have stuff?
No, because, most of the time when you give us problems, it has whole numbers. I don't think you've ever given us a problem without whole numbers that I can remember.
I would not say that. On your problem set, you had one. Where your zeros were fractions. Yes. Go back up to the beginning. How many sign changes are in f of negative x? F of negative x. There are no sign changes in f of negative x, which means, should we have tried a negative value to begin with? No, because there's not going to be a negative 0. But I wanted to show you what it looked like, and I wanted to see if anybody would stop me before I did that. Okay? Always think about Descartes' rule of signs. I didn't go through it on this example on purpose. Okay? I wanted to see what you would pick out from it. But list, if I give you like an open-ended problem, find the zeros. Okay? List the possible rational zeros. Think about Descartes' rule of signs, and then use the upper and lower bounds if you want to. Okay. Before you start listing the possible rational zeros, it is okay for you to factor any of these problems if they are factorable. I am always okay with you factoring if it works, because it is going to take less time. Okay? So we're going to go through one more example where we can tie everything together. And I want to point out how you might be presented to write your answers. Okay? Also, it's something that some of us missed on the problem set, so I want to make sure it gets straightened out. Our possible zeros. Factors of our constant over factors over our leading coefficient. This is a nice list, isn't it? They're all integer values. That is nice. Now, Descartes' rule of signs. How many sign changes are there in f of x? How many? 4. So there could be 4 positive zeros. There could be 2 positive zeros. Or there could be 0 positive zeros. However many sign changes there are, just keep subtracting 2 until you get to either 1 or 0. Okay? Negative zeros. F of negative x. X to the 4th is going to stay positive. X cubed will change to positive 2x cubed. X squared will not change its sign values. Negative 8x will become positive 8x, and then we have our plus 4. How many sign changes are in f of negative x? Okay. We will not have any negative zeros. So let's not try negative 1 or negative 2 or negative 4. Okay. We always like to start by trying 1. Some of you are going on without me. Go for it. Test 1 out for me. Does it work? Hey, all right, 1 to 0. Okay. Now, what this problem is asking us to do is not only find the zeros, but also write f of x as a product of linear factors. So we're going to focus on the zeros, and then we'll talk about what the product of linear factors looks like. Okay? Suggestions on where to go from here? Sorry. Okay. X minus 1 is the factor we get from our 0 of 1. Left over is x cubed minus x squared plus 4x minus 4. Yes?
Couldn't you also just divide by another one of your possible since you only have 2 left?
Okay. I'm really glad you brought that up. Okay? I will come back to this. You do have 2 options. You can look to see if this factors, okay? If you see a pattern, if we have a cubic, we can only factor by grouping, really, if we have 4 terms. So if you see that pattern, go for it. If you don't see that pattern, we are going to have to do synthetic division again. Now, I'm glad Caroline brought up, can't you just try 2 or 4 because you don't have to do one of those 2. Actually, just because we tried 1 and it worked, doesn't mean we can cross it off of our list.
It's because you got 2 positive zeros and then
Well, no, because a lot of people are going to do that. They're going to say, oh, 1 worked, I'm going to cross it off. But we know it's possible to have multiplicity of 2 or 3 or even 4. I mean, we can have multiplicity of more than 1 with our zeros. So just because you get a 0 that works doesn't mean you can cross it off your list. Okay?
Would the 0 count for also?
Well, this is positive. Okay? So, we can either do synthetic division again, or we can factor. It doesn't matter. Okay? I've already drawn up my synthetic division, so I'm going to do synthetic division again. And since We can't really cross off 1. Let's try 1 again. Okay. Some of you are factoring by grouping, and I think that's great. But see how we got a 0 to work more than once. Okay. So we have zeros of 1 and 1. Left over we have x squared plus 4. Can we factor x squared plus 4? Right. We could factor x squared minus 4, and technically, yes, we can factor x squared plus 4. But to find the zeros, you're going to want to set x squared plus 4 equal to 0. X squared is 4, negative 4, excuse me, which means x is plus or minus 2i. Some of you can see that without doing the work. That doesn't bother me. Okay? Store zeros. Our zeros are 1, 1, and plus or minus 2i. When it asks you for the product of linear factors, okay, you need to give me x minus 1 times x minus 1. It happens twice. You can write it twice or you can square it. X minus 2i, x plus 2i. If we multiply all 4 of those out, we would get back to where we started. Anytime you notice that you can factor, do so. It is a possibility that you get down to a quadratic and have to do the quadratic formula, but I don't want you to feel like you have to do the quadratic formula all the time, because if you can factor, it works out nice. Okay. All right, you do not have a very long assignment for tonight. Now, notice the order in which I gave you these problems. I gave you 90, 91, and 93 first because I want you to do those first. They're the Descartes rule of signs, just saying how many positive, how many negative real zeros do you have. I want you to do those problems so you can apply them to 67 through 82 up there. Okay? And you're doing these. Make sure on 82 I don't want you to use a calculator. Or really on any of them I don't want you to use a calculator. Okay?